principle that's behind the proof of this, and that's called the pigeonhole principle. And the pigeonhole principle says the following. You take n pigeons, and they're trying to go nest into m pigeonholes. If there are more pigeons than pigeonholes, then 2 of them better share. Okay, 2 of them have to be in the same pigeonhole. Okay, this makes sense, right? If you have 101 pigeons and 100 pigeonholes, 2 of them are going to share. So let me give you a simpler application. It turns out Shor's theorem, the one I gave you, is really an application of the pigeonhole principle. Not an easy application, but quite a clever application. But I'm going to give you a different, much easier one. And it's the following. If I take that number grid, again, the 1 through 100 that we looked at, and you color them red or blue, as we did, then there has to be a rectangle. Consider it drawn the way I drew it on the board, on the screen before. There has to be a rectangle so that the 4 corners of that rectangle are all in one color, either all red or all blue. Okay, so for example, if I looked at the bottom part of here, I'll give you an example of a rectangle right here at the bottom, the rectangle that's connecting 75, the 4 corners, 75, 80, 96, and 100 here are all blue. What it just says is somewhere in that grid you will see it. So I'd like to give you a full proof of this statement. It's really just the pigeonhole principle. So here's some coloring. You could do this with any coloring you wanted. I flipped the coins in red and blue, some of them. And it turns out to do this, I don't need to look at all the numbers from 1 to 100, but I'm just going to focus in on this highlighted part, which consists of 27 numbers. It's most of the numbers up to 30, except I left off 10, 20, and 30. And what's important here? It turns out it's not important which numbers I colored at all. But what's really important is the patterns of reds and blues that I see in there, the triples. So that first one is blue, red, blue. Forget about the fact that it's 1, 11, 21. That's extraneous information just harming you for solving this problem. Okay? The second pattern is red, red, blue. So we'll copy them down at the bottom, all of these patterns. There's red, blue, red, blue, 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 red, red, and so on. Okay, I'm going to copy down all of these 9 triples down at the bottom. Okay? Now, I've just told you I have 9 triples down at the bottom, and each of these triples is colored either with reds or blues. How many different ways can I color a triple with reds or blues? Well, I have 2 choices for the first guy, 2 choices for the second guy, 2 choices for the third one. So it turns out there are 8 choices for how I can color these triples, 2 times 2 times 2. But I have 9 here, because I carefully chose 9 triples, which means 2 of these guys better be the same. That's the pigeonhole principle. Okay? And now we're almost done. In these triples, there's only 2 colors that are used. So there's either 2 blues or 2 reds. There might be 3, but there's at least 2 of one of those 2 colors. That's another use of the pigeonhole principle. So let's restrict to those 2 blues. Okay? And then connect them up, and you see the rectangle at the bottom, and then therefore you see it up at the top. So what I did in this, I got rid of all the extra information, and I just looked at what I really needed to know, and to prove this is just the pigeonhole principle. So what I've proven is that if you put this rectangle anywhere, any 27 numbers in it, you will find one of these triples. So there it is in that one, and I could move it elsewhere, and you will still see it. Okay? There should be a rectangle. Okay, it's just the corners of the rectangle. So even though this was just sort of supposed to be a random coloring that I obtained by flipping coins, there's actually a lot of patterns in there, and patterns that are on the corners of these rectangles. Shor's theorem that I gave you is a more complicated use of the pigeonhole principle that you have to be much more careful. And even with 2 colors, it's a more complicated proof, but it's true for any number of colors. Okay. So my field is actually not combinatorics, which is the type of problems I've been telling you about so far, very combinatorial. Can you find patterns? What do you see? My field is actually dynamics, and in dynamics what we do is we study certain systems and how they evolve with time when you keep repeating and doing the same thing in the system. So I want to explain to you that there's actually a connection between this looking for patterns in integers or elsewhere and dynamics. So I've brought back the circle here. And what I'm going to do on the circle is I'm going to rotate around it at a fixed speed and go down until I've gone, this is 3/8 of the way around the circle. And then I'm going to put down a dot. And I'm going to continue now and rotate again 3/8 of the way further around the circle. So that's 2 alpha. And then 3/8 of the way around again, 3 alpha. And I'll keep going around. Well, I did this by going 3/8 of the way around the circle. Eventually, at 7 alpha, what's going to happen when I keep going? So I'm doing the same thing each time. I'm going to go 3/8 of the way around the circle again. Well, it turns out I'm going to go back to 0, and I'm going to repeat. Okay? Remember at the very beginning, we talked about things that repeat. This is another example of periodic behavior. Okay? Because what I'm doing is I will never hit anywhere else on the circle, no matter how long I keep waiting and going around and around and around, going by 3/8. I'll keep going through these 8 dots. I will never add anywhere else. But thinking about the circle is quite hard. It's much easier for mathematicians. We like to think about things that are one-dimensional. Circles are sort of two-dimensional by their nature. It's not, as I just opened it up, I showed you, it's really a one-dimensional guy. Okay, so there's that circle up here. Let me do the same thing down here to justify why I would call that alpha 3/8. Pretend that the length of this interval is 1, between 0 and 1. When I go 3/8 of the way, this is exactly length 3/8, and do the same thing, I get the exact same behavior. And now I'm just adding 3/8, add 3/8 more, that's 2 alpha, so 6/8, and then I add 3/8 more, I fall off the end, so just subtract 1 to bring myself back here. That's what was happening up in that rotation. And what you'll see is I'll get up to 7 alpha rather. Okay, and you can do that as 7 times 3/8 and subtract off the integer part, which will bring you back into this interval, just like you were rotating around up here. And if I continue, I will always see the same thing. So this is why it really makes sense to call this a rotation around the circle. I was rotating by 3/8. Okay, so we could stare at this for a long time, but it would really just keep going on and doing the same thing. What if I take that and I don't just go 3/8 of the way around, but I move it a tiny bit? Okay, this is some other beta. It is not a fraction. It is not written as p over q for any integer, p and q, any integers p and q. It's an irrational. And now what happens if I do the same thing? Here this length is beta over the way between 0 and 1, and I'm going to add another beta, so I'm going to go to 2 beta and to 3 beta and continue going around and see what happens. And you could ask, well, am I ever going to come back to exactly where I started, and so that I will see this periodicity, or will it keep going? So remember before, when we went up to 7 times it, this beta was really close. When we went up to 7, we came right back to 0. But here I come a little bit after, because beta was a little bit bigger than the first 3/8 alpha, the alpha that was 3/8. So what happens if I keep going? Maybe it'll just take me longer. Okay, maybe I'll keep going on and on and on. So it's going to go, and it's going to keep going around. Each time I'm going a distance beta and dropping another dot, another green, the red dots will be added in, and I'll speed it up a little bit. So, because otherwise we're going to wait here a long time for it to come back. Okay, 21 looks pretty good. It comes really, really close, it turns out. But let's see. And so you could ask yourself, well, what are the patterns here? When am I coming back? What am I doing? Will I ever come right back to yourself? And you'll see it's really going to fill up the circle. Okay, so I hope you believe me. It looks like these dots are never overlapping yet. But they really are beginning to look like they're going everywhere, and you're going to run out of room. So the next one better land on something that's already there. Maybe? Okay. But what's really going on when you zoom in and look, it's still going. Okay? There are still holes there. It keeps putting down another dot, and there's always room for it to keep putting down another dot. So you see the green is coming by every once in a while. Okay, it has the whole way go around the circle, so it's still going, and it should eventually put a dot finally up there. And it will continue putting a dot at some point. We shall see. Eventually it'll come. I hope put some more dots down. And what's going to happen is it's going to fill in the dots. It actually does so in an extremely regular pattern. It turns out that it fills in the dots alternately, one over here and one down here as they get closer and closer to 0. And it turns out that there's only, at any time, there's only a very, very few lengths that you see there. In fact, only 3 lengths at any given time between the dots. And so eventually when you keep iterating this over and over, this thing, it looks like you've really filled everywhere up and it's still going. Okay? But you can't see that anymore because unless I would zoom in again to see this. So it turns out there's actually quite a lot of patterns hidden in this. And so I'm going to try to explain to you that there's a lot of patterns hidden in these times here. Before we do that, let's go back, first of all, to the rational one, going by 3/8. What I have done here is I have colored the first half of this interval blue, from 0 to 1/2, starting at 1/2, including 1/2, all the way up to 1, I've colored it red. Now, 1, you'll notice, is blue also, because 1 and 0 up here, they're the same thing, they're 0. So 1 and 0 in this interval down here are identified, they're the same point. So I've done the same thing up at the top. I've colored this blue, the bottom is red. The point 1/2 is right here, that would be colored red if I labeled it. And now I'm going to look at what happens to when I start rotating exactly by this rational, the 3/8. What happens when I go around? And what I'm going to label is, you started at 0, so I'm labeling that 0 because 0 was colored blue. Okay? I'm going to label the whole top half by blue zeros and the whole bottom half by red ones. So the first time I went around, I stopped up there at 3/8. It was also blue. Okay, so that's why I stuck down a blue 0. It was in the top half. But the next time I went around, in the bottom, this was 2 alpha. I was in the bottom half, so I'll make that a red 1. So did everyone see how I'm generating the zeros and ones from this? Okay, it's just depending on whether I fell into the top half or the bottom half of the circle, or if you want to think about it as the top half or the first half or the second half of this interval. Okay, now, remember what we learned about this guy, the rational guy. Once I went around 8 times, it just repeats after the first 8 iterates. So now I can fill in the rest of this. In fact, I don't even have to follow around and see. What I could do is take those first 8 numbers and copy them over, and just they would already be there. I knew what they were before I continued iterating. Right? So what I'm saying is that there's a window here, and the window looks like 0, 0, 1, 0, 1, 1, 0, 1, such that I can move that exact window over, and in my coding of this rotation, it's exactly the same window, 0, 0, 1, 0, 1, 1, 0, 1. And I can keep moving it over, and it will always be the same. Okay, so you could ask, does the same thing happen with the other guy, the irrational? Oh, what? I got one more comment before I go on to the irrational, sorry. It turns out, remember what these corresponded to. This was what timing at 0. This was the first time I rotated by 3/8, the first iterate, the second iterate, and so on. Turns out, remember that Schur's theorem. There are lots of patterns here that you can see inside one color. For example, 3 + 6 = 9 is all in one color. Okay? And it turns out you can use dynamics, this idea that you get things always staying in the top half or the bottom half, and you have to be much more careful and say they always stay even closer than just the top half and the bottom half to prove Schur's theorem. But it's a flavor of how you would try to do it, is to look for these. I'd like you to take a look at the triple, let's see, I think 19 + 3 is equal to 22. That's another blue triple. I didn't write it down, but it's another one. Just to keep in mind, if I had taken 3 + 19 = 22. We'll see that one maybe later. Okay, now let's play the same game, but with the irrational guy. Okay, so I'm going to go by rotating this time by beta. I started at 0. I stayed in the top half because beta was really close to alpha. Remember, I've just moved it a tiny bit. And now I'm going to move it around and check out the coding and see where it goes. And it looks quite similar at the end. 0, 0, 1, 0, 1, 1, 0. And that is the first 8 of them. So 0, 0, 1, 0, 1, 1, 0, 1. Let's do the next 8 and see what happened. Remember, it's very, very close to that alpha, to the rational guy. And so it's going to look extremely similar for a while, but at the end, it actually changes a little bit. There is no pattern. If I tried to use the pattern of length 8, the window of size 8, to copy it over again, it wouldn't work. It would be a mistake at the end. But maybe you could ask me, well, maybe the window of size 8 was the wrong window. Maybe there's a window of size 1 or of 2 of our 100 that actually works. Well, we could check, does 1 work? And it turns out no, because you go 0, 0, and then it's a 1. You can't copy that one over. Does the window of size 2 work? No, it fails right away. The first window of size 2 is 0, 0, and the second one is 1, 0. Does the window of size 3 work? 0, 0, 1. If you tried copying that, you'd get 0, 1, 1. Again, a mistake. And you can keep going, 4, 5, 6. You can check them all. 8, it looks like it works, right? It was really close to alpha, but then again, 8 also fails right at the end because it's 0, 0, 1 at the end instead of 1, 0, 1. Turns out whatever you tried to use, 9, 100, 1,000, it wouldn't work. It might look like it worked for quite a while, but then it would not. But in spite of that, if I'm looking for these triples that have really nice properties in the sense that they're all in the same color, 3 plus 6 equals 9, they're there still in this one. And remember I told you to look at, let's see, 19 plus 3 is equal to 22. That's another one that's still there. But right over here, in the end, there are ones that happen in the rational guy and do not happen here. Okay? But the important point is that however I did it, it turns out there are still these triples, like the triples from Schur's theorem, that are always there, always in one color, these triples. Okay. So let's look at that sequence. This is again the sequence that came from the periodic guy. And so what it turns out to be true is if I copy down all the patterns in the windows of size 8, you would see all of them. Okay? So here's the window of size 8, and I'm going to slide it over one by one. We already saw if we slide it over by 8, I'm just going to get the exact same thing. But if I slide it over by 1, I get somebody new. Slide it over by another one, I get another new one. And so on. If I keep sliding it over, it turns out there's going to be 8 different windows of size 8 here. Okay? And those are all of them now we know because when I got here, this guy is the exact same as the first one. Right? So I'm not going to see any more of them. So that's what happens, it turns out, with any periodic sequence. There's always a window like this that I can slide over, slide over, slide over, and there'll be some number of times that I can see it, and then there's no more of that. No more patterns. So these patterns, both of them appear, right? They're the same ones we see.